We continue today the exploration of the application layer. And we'll explore the DNS. So the DNS is also not really application layer, although formally it is. We all know it. We know what it does. The goal is to map names to IP addresses. The names are organized from a hierarchy of names. At the origin, there were, at the top level of the naming system, there were only three-letter domains and two-letter domains. Two-letter are always countries, and three-letter originally were the first domains, like .com was for commercial, edu for educational organizations like universities. In practice, later, this was extended to practically anything. So if you're willing to pay $500,000, you can buy your own DNS top-level names, like companies like banks or large international companies like Nestle could buy their own domain if they want to, if they're ready to pay a huge amount of money every year to renew it. There's also a special domain that we'll discuss a bit later. So two-letter domain names are often used, for example, bit.ly of Liechtenstein. They are used for other purposes, but they are truly domain names. For example, if you use a .ly, like you do often for short URLs, you're actually using a name that belongs to Libya. Whether you are happy with that or not, that's another system. How does the DNS work? Well, we have in our machines, in your smartphone, in your computer, every host has a piece of software called the DNS resolver that will translate any name to an IP address. For example, if you click on a URL of this nature, then the first element of the URL, www.zurich.ibm.com, must be translated by the web browser to an IP address. We've seen how to do this in the socket by using get host by name, for example. That's what the socket library will return to you. So how does it work? Well, how does the implementation of get host by name work? Well, your name resolver, so the implementation of get host by name, will analyze this and will see it, and will first ask a query to its home DNS server. The home DNS server is the one that we are configuring our IP system with. By default, it's an EPFL DNS server if you're at EPFL. And this DNS server will receive a message, which is explained here. That's a DNS query. We can look at it in Wireshark. We will see exactly what I'm displaying here. We will see a DNS query with RD equal yes. RD is recursive, whether we want this query to be processed recursively. Processed recursively, that means that we would like the server to do it for us. So the server will take this request and will try to solve, and we'll do a number of steps to solve it, and only when it's solved will send us a reply. That's what the recursive means. Now the DNS server, assume here, doesn't know anything about this. It's the first time somebody at EPFL is asking for such a name, but it knows it's IBM.com. The DNS server is pre-programmed with the IP addresses of all the top-level domains. So in the previous slide, I was showing the top-level domains. So all those top-level domains have domain servers that know about those domains. So it will send a query to the what is called the root name server. So it's one of 13 name servers in the world that cover the top-level domains, and will receive a reply. Now the reply will simply contain this. What is this? It is the IP addresses of DNS servers of the IBM domain. IBM, like EPFL, has a domain, ibm.com. EPFL has epfl.ch. So if we create your own domain, you have to create a database, a file, with all the IP addresses of all machines that are in your domain. So IBM does that, and you need to publish also what is the IP address of, here there are 3 IBM DNS servers. Obviously, you want more than one in case there is a failure somewhere. And this is the information that we have obtained. So all of this is written in the DNS. In the DNS, we have records that are called NS, which stand for name servers. So at the end of this step, the DNS server of EPFL still doesn't know the answer to the query, but knows now the IP address of the DNS server of IBM. Then it will send the query to the to the DNS server of IBM that will provide an answer. And this answer is now simply forwarded back to the host here. Now, this DNS server of EPFL, when it sends a query to the root name server or to the DNS name server, has recursivity equal no. That means we don't expect those guys to do the job for us. If recursively would be supported, here the root name server would do the job of contacting Watson, etc. But of course, you don't want the root name servers nor the servers of companies to do it for hosts that are not in the companies, except if you're Google and you're happy to devote your huge infrastructure for people to keep the traffic going to you. But EPFL doesn't do that. So if someone else joins, for example, if an outside server, somebody somewhere in the world wants to know what's the IP address of corresponding to a name at EPFL, the DNS server of EPFL will not support recursivity. It will simply say what it knows, and that's the end of it. The DNS files are simply big text files that contain what is called records. It's not a true database in the sense it plays the role of a database in the sense that it's a set of records and we want to ask questions to it, but it's not a true database in the sense that it's just a plain text file. You don't expect to do searches. You don't send SQL queries to a DNS server. So this plain DNS file you can get it entirely, or you can get pieces of it by using DNS Lookup, or here I'm using dig to send queries. For example, here I'm asking what is the IPv4 address of this name. So v4 means an A record, A like address, and v6 is quadruple A because it's 4 times bigger address here. So if I ask for an A address, for an IPv4 address, I will get this type of answer, which gives me the address, and also another records type, which is CNAME. CNAME is canonical name. It is an indirection where a name can be mapped to a name. In principle, you want to map it to an address, but you may want also to map it to a name. For example, here we have a server that is publicly known name, that is in fact working on some other machine, LCA1 SRV2, which is the current name of the machine in which this server is hosted. And this may change as this machine may be allocated or not to this service. And this is a way to support such allocations here. We see A records that gives IPv4 addresses and quadruple A that gives IPv6 addresses. The DNS can be used for essentially A and quadruple A record, but there's a large number, close to 100 other records type. One that is very frequently used is also MX record. It is to find what is the IP address of a mail server that serves a given mail domain. So if I have an address name @epfl.ch, I expect to find the IP address of the mail server or a name of the mail server of one of several mail servers. Of course, this will need to be translated to an address by finding, hopefully, an A or quadruple A record. So that's an example of a service, mail. There are zillions of services. For example, one that is widespread in practically every enterprise network is IP telephony. So IP telephony uses servers and the names of the standard services associated, depending which protocol you use to do IP telephony. Those are the 3 standard ones. H323 or SIP, and in principle you use SIP over TLS. So if you want to find what is the name of the server that supports essentially the directory services used by telephony, then you have to go to this. And you have more. You have, for example, each of the telephones as EPFL has an IP address for telephone, and that is also put in the DNS. I showed how the DNS worked by assuming that the local DNS server had never seen the query that was sent, query to IBM.com here. Of course, once this query is received, it is kept in a cache because it is expected that if somebody is querying for this name, it's probably, or at least most names will be used many, many times. So there will be a lot of reuse of the names. So the DNS uses caches. That's a big difference with databases, as we will see. The cache means that when this DNS server of EPFL has had the succeeded in getting the IP address, a successful answer to its query, it keeps it in a cache. How long does it keep it in a cache? For as much as indicated in the field of which is the time to live. Now it's a true time to live, unlike the TTL in IPv4 packet. DNS records have a time to live, which says how long you are expected to keep this information. For example, IBM here is using 2 hours. That means that this server will keep this information for 2 hours. So 2 hours after, roughly speaking, 2 hours after the first query to this name, whenever there is another query inside EPFL, this will not trigger outside traffic, but it will be served locally, which has a side effect. If in the meantime the name changes, if IBM has changed the server allocation or the server failed and another one took over, so the name to IP address mapping may have changed, then during those 2 hours, the information here will be incorrect. You will have the old address. That's how the DNS works. There's no way to solve that problem other than giving a very, very small TTL. You might give a TTL of a few seconds. We will see some systems that do it. Google typically does it, or Facebook. But by doing this, of course, you control the amount of traffic. So if you are a company like IBM, which is not in the business of providing cloud services, then you don't want your servers to be flooded with a huge amount of traffic. So you might give a TTL of 2 hours. That's also what EPFL does for its own names here. So unlike in a database, when you ask what is the value of this record, you will have the most recent value, including if you're trying to book a seat, if the seat has been booked 1 second before your request by someone else, then the database will implement consistency. That's one of the primary goals of a database. Here, we don't try to be consistent. We try to be lightweight and to scale to the entire world, which the DNS does. And the price to pay is that if you go from Infomaniac to Switch, for example, to host your DNS server, the change will take some time to become visible to the entire world. There will be a period of time where the things may be incorrect, and you have to live with that. So if you're changing your server from one IP address to the next, you still need to keep the old one going for some time, because by the time you've done the change, not everybody will be informed through the DNS here. So we see that when another query comes from another machine here, it will receive a time to live which is smaller here, because that's the time to live since the time elapsed since the first receipt of the answer here has been subtracted here. And after 2 hours here, the cache entry will become stale, and the server here will not take this value, but will go back to the source. We've done a lot of trace routes, hopefully. And when we do trace route, we see things like this. Here I'm doing a trace route to this domain name here, and my trace route software will display this. We know how trace route works, right? It sends packet with increasing hop count or increasing hop limit or increasing TTL. And the TTL too small error generates an ICMP message, which is interpreted to know who is in the hop. So that's the first machine, the first hop between my host and this destination. But what we see is the name of the machine followed by its IP address, at least in this version of traceroute here. How do we believe that the software gets the name? Well, by doing what is called a reverse DNS lookup. What ICMP will give when there's an error, TTL exhausted, it will send the message back to the source. So what the traceroute software sees is the IP address of the router who sends this error message. It is the software, it is the traceroute software that goes to the DNS to find what is the name that corresponds to it here. The name, as we know, is not in IP packets and is also not in ICMP messages here. That's not the goal of such protocols to serve such thing. How do you believe that traceroute does its DNS lookup? I close the poll. The majority says B, which is correct in some sense, but what question is asked to the DNS server? The DNS server is something that has a list of records, and as I said, it's essentially a plain text file, and the only thing that the DNS server does is, if you give the type of record, it will answer and find so it will search by type and target here. Now, ideally, we could think, if we have a database mentality, you could do an SQL query to a database and say, give me all the records that have IP address corresponding to this. So we need to search by IP address field rather than by DNS name field. This is not the way it is done. Again, it's not the way it's done because the DNS has been thought of as a plain text file that you can search by record type and target. The target of an A record is a name, not an IP address. So the system is organized such that it's easy to find a name, but difficult to find an address. Because of this, in the DNS, we ask the domain managers to populate reverse records. A reverse record is a domain in the domain IN address for IPv4 address .arpa, which is a special name followed for that, where every IP address corresponds to one entry, one record, and this, in some sense, we force the database, the file, the zone file, to contain the reverse mapping. So if you do a mistake in this reverse mapping, if you do it manually, probably there will be a few mistakes. Nobody will check for it. So you might receive IP addresses that DNS names that do not correspond to IP addresses because those two things are done separately, and there is no consistency check by the DNS itself. Hopefully, good software does a consistency check when you write your own file, but that's what you have to trust. So there was in the past a number of attacks against the DNS where people were injecting false reverse records. They were called the pointer records, the PTR records. And so that if you would ask if you would do a trace route, you would obtain the correct IP addresses, but wrong names because they were not correctly done here. This is, for example, this kind of things. If you would search for this address, you would find funny names like Freedom to the Galaxy, which was simply due to this lack of consistency. So that leads to the question, who owns the names and who puts the names here? Well, it's hierarchical. At the top, there is an entity that is delegated from, at the beginning, from ITF, then now the public political entities, United Nations, and so on, have interfered with that. So now, right now, there is a company called PTI, Public Technical Identifiers, which was formerly ICANN, that runs the top-level domain. So if you want to buy Nestle, you have to ask them, and if a country splits into two and each of South Sudan becomes an independent country, it needs to find a country code. So this is this entity that will manage all of this here. And will also delegate to a number of private companies the running of the 13 top-level DNS servers here. Now, this domain in particular has, there is a domain called CH for Switzerland. So this entity has to find someone in Switzerland with agreement of the Swiss government who owns the political aspect of it. It's called a registry. So in Switzerland, it's Switch. Switch is the entity that serves as an internet service provider for the public arms of Switzerland, so for the government, for the university. And it is also the one that has the authority about the name. So it's a purely legal authority. In addition to that, there is a practical thing which is done by the registrar. Register is a commercial organization that has obtained the right from the registry to sell the names. So you can go to Infomaniac. A few years ago, this was the two roles were the same. So you could go to Switch to buy and domain names. Now you can go to Infomaniac or even non-Swiss companies to buy Swiss domain names here. So this is about buying the name, just renting for every year a domain name. In addition, you put the name in, you need to put the name in a DNS server, which can be a separate thing. You can buy your name for Infomaniac and put it in a DNS server run by ZoneEdit or whatever, or you buy everything from Infomaniac, which is simpler here. So this is, and it's the register, for example, that sells to EPFL the name .epfl.ch, for which EPFL pays 14 francs every year. And if they forget to pay, then they might lose the name, and then it would be very embarrassing. And then once EPFL has received epfl.ch, inside EPFL, there's a similar organization, the computer infrastructure of EPFL runs the name system of EPFL, which means running the DNS servers of EPFL, making the files that I mentioned that contain all the records that correspond to epfl.ch, and providing also rules and regulations for what names are allowed inside EPFL. For example, one rule inside EPFL is that we don't have subdomains. You can have lca.epfl.ch, but you cannot have mypreferredproject.lca.epfl.ch. That's one of the rules of EPFL, for example. ETH, which is bigger, has two levels of domains. So you can have lca.ee.eth, z.ch, for example. So this is how the hierarchy works. At every level, there's an entity that owns the domain, and then it does what it wants, and it may delegate to sub-levels or not. There's a number of self-organized domains that are emerging. One based on the blockchain, Bitcoin blockchain technology is called Namecoin. So it's an attempt to provide peer-to-peer DNS names for the domain .bit. So as we have seen, this is very hierarchical. So it's in order to get a name, you need to go to an owner of the domain who has been received it from delegation of another party, and so on. If you want something completely peer-to-peer, you could use blockchain technology to do it. It's not a real success. I haven't seen much of it being used, but perhaps in the future, that could be an alternative to that kind of system. The DNS was originally motivated by the need to not type in IP addresses. For example, when the web became public, all of a sudden, pizzas in California started having a DNS server. Of course, they didn't want to type in EPFL addresses because that's not something for the general public. Now, But in the meantime, DNS has found a lot of other uses. It's not just hiding IP addresses. It is really used for a number of things that we will see today and next week. One of them is load balancing. If you have a company, softcom.com, that is providing a web service here, and imagine Google or Facebook or whatever, you type google.com, and then you don't go to one server called google.com. You go to one of hundreds of thousands of servers called google.com here. So how can we, DNS can be used to facilitate the management of something by putting in the DNS a large number of IP addresses. Typically, it would not be done exactly in this way. We would typically have a canonical, a CNAME here that would correspond to different names. But to simplify the story here, I'm just assuming it's mapped to a large number of different IP addresses here. And then you see also a very short time to live, 300 seconds. 300 seconds, yes, so a few minutes. It can be even much shorter here. So this has the effect of what is called a load balancing DNS server, because that means that when your system will go to the DNS server of Softcom, then the DNS server will reply with one or a small number of these mappings here. So it can control in this way whom you will connect to. And if the TTL is very short, then it can really adapt to the load on the server. So when you go to google.com, you go to a server that's perhaps in Ireland today. If you do it 20 minutes later, perhaps your server is in Zurich. So this will be controlled by the DNS of Google that will use this here. Of course, you need a very short TTL, which means also that those servers, those DNS servers, become monstrous entities. They will have a lot of traffic to run. So those big companies, Facebook, Google, etc., they usually have server farms just for DNS. In fact, one of the famous outages of Facebook last year was a problem with the server farm of DNS servers of Facebook here. The DNS I've shown does not speak of security, so of course it is easy, and in fact the little funny attacks that I showed where we inject pointer records into the DNS were possible because the domain that owns those addresses were not secured. So another one, you and me, you could inject into the DNS pointer records for a domain that we don't own. And if there is no security, it's completely possible. That's for pointer records. It could even be worse. You could inject epfl.ch A or quadruple A records. That means you could capture all the traffic that is intended to go to EPFL. That would be the first step into mounting an attack against EPFL, for example. First, you get all the traffic to go through you, so you can analyze and read and try to see passwords that are sent in the clear, etc. Of course, this is not satisfactory. And today, most systems, or many systems, not all, but many systems, use what is called DNSSEC, which means that in the record that I've seen that contains the reply from the server contains a signature. And this signature is using something similar to the RPKI that is used for routers, is for BGP, uses root certificates at the root servers of DNS, the 13 root servers, that signs the certificates of IBM, for example. So when the server from EPFL receives a query reply from the DNS server of IBM, it can verify the signature. So this is what I would say most enterprise, not all, but many enterprise networks do, probably most enterprise networks and many public organizations here. So large companies like Google do it systematically. In addition to this, some software also starts using DNS over TLS instead of over UDP. So a DNS query is typically sent over UDP, which makes a lot of sense if we ignore security. because using TCP for a single message that fits in one packet is an overkill. So we send a packet to the DNS server, we get a reply. So we don't even need to do the stop and go protocol for reliability, because the nature of what we do asks for an acknowledgement, which is the reply. If I don't receive an acknowledgement within a few seconds from the DNS server, I can assume the packet was lost, or the DNS server is too congested anyhow. So it typically uses UDP, but it's not secured. So if you want to have security, you can use TLS, which is typically over TCP, which means that your client first goes to the burden of opening a TLS connection over TCP, which we have seen is expensive. Over QUIC, it's less expensive. So we see more and more DNS software being done over QUIC. So if you have a Chrome machine that uses a Google server, probably all the DNS queries are sent over QUIC here. So this will authenticate and encrypt the query between you and the server. And in particular, it will be a way that is sometimes simpler than this to authenticate the local server. Because the DNS servers, this kind of authentication is essentially between DNS servers. The DNS server of EPFL, when it contacts the DNS server of IBM, it can know that the reply is truly coming from the DNS server of IBM, and the record was injected by IBM, not by someone else. For you and me, for our devices here, it is easier sometimes to use TLS because we are equipped with, that's the kind of things we do for e-banking and so on. So we're equipped with the certificates. We don't need to go to those special DNSSEC certificates. When you send something to your printer, you might send something to a name like this here. So does it mean that my printer is in the DNS? Well, in print, it could be if you use a special DNS to do things like this, but most of the time it is not. There's a special domain name, which is called local, which is not in the DNS server. Instead, it is available for things, for objects or services that are in the same local area network, in the same subnet in IP terminology. So for example, if my printer is in the same subnet as me, then I can discover it. If I know the name, for example, I could have first I could discover it by using protocols like universal plug and play or other similar things. This printer will once in a while send a multicast packet in the local area network saying, I am this, and I will remember, my device will remember it. If my device has forgotten, it will resolve this name to an IP address by sending a DNS query to this multicast address, which is a local scope multicast. That means this multicast will never be forwarded by routers. So that is how home networks typically are bridged. So they are a single local area network, and multimedia servers and so on use that kind of things. So you might wonder how comes you see names? Well, that's the answer. So we see here the two ways of discovering names, doing mapping. We've talked about ARP. ARP typically uses that kind of things, does broadcast or multicast in the local area network. The DNS instead uses servers. And when you do DNS in the local area network, well, you also do the same trick as ARP. Okay, a little quiz here. Here I'm assuming that EPFL names have TTL of 120 seconds, as we see here, and assume all DNS servers of EPFL go down. How long does it take for the whole world to become unable to reach EPFL services? I close the poll in a few seconds. Closing. And of course, the answer is B. That means because all the cache, if an entry is not cached, then the service is unreachable. If an entry is cached, you still have the IP address of the service. The DNS server doesn't work, but the EPFL servers do work. So during an interval that's between 0 and 2 minutes, you're still able to reach the EPFL services. But after 2 minutes, then all the caches here will become stale, and you will not have the IP addresses here. This is what happened to Facebook last year. So that shows that if you put very short TTL, then you have to make sure that your DNS system is constantly up and running. Right? So that's why companies that don't provide cloud services, for example, or huge data infrastructure, but simply want to show presence on the internet, may have much larger DNS caches here, because I mean, bringing your server down for a minute is something that can happen, for example, during maintenance. We switch to another topic, application layer gateway. So the term gateway, we see it always when we look at configuration. Default gateway is the name that is used in IP configuration, but it means router. When the internet was created, before IP and TCP, there was the NCP protocol that was store and forward, and the word gateway really alludes to that fact. When IP was created, they kept the word gateway, but today it's obsolete. It's still visible in a number of documents. But gateway, typically today, really means at a layer higher than the network layer, transport or application gateway. So an application layer gateway is an intermediate system of the application layer. For example, a web proxy that sometimes exists in some companies. If you go to private companies, if you visit a private company, probably if they give you access to their company, if you do a semester project or a master thesis there, if they give you an access to the network of the company, probably in many companies, you don't have direct access to the internet. Instead, if you try to browse the internet, you first go to a gateway that will or will not allow you to do what you want to do, because you're not supposed to go shopping your next shoes while working, for example. So you might need for your work to access some services, but here the gateway will be between you and the final service. How does it work? In a very simple way that's illustrated here. When you open a TCP connection to the gateway terminates the TCP connection, so gets all the interaction. For example, the GET message here will be obtained by this gateway logic software that will decide or not to simply forward it, might kill the message if they don't like it or it violates policy. If it does not violate policy, it would simply forward it to the true destination. The data will come, and the data is piped here. So if we look at it from a socket viewpoint, the software that's doing the gateway logic has a socket that goes towards A and a socket that goes toward B. And if it accepts all the data, the only thing it will do is simply create a pipe in between the two sockets. Anything that's coming on one side is repeated on the other, and vice versa. So there will be two TCP connections. Primary goal is often to filter traffic. Sometimes it's also for performance, because here we have two TCP connections. So that's a trick that's very often done by cellular telephony operators, because here we know that if you connect with TCP to a server that's far away, you will probably have bad performance if this link is lossy, because of the problems of TCP reacting to losses, and this will be amplified if your round-trip time is large here. So one way to get this is to break the two TCP connections. So you will have perhaps bad performance here, but since here you're sharing the link with only the customers of Swisscom, for example, and perhaps a small number of users, so the sharing here will first can be controlled by Swisscom, and second will not be too bad for you because all the others also might have similar losses here. So the end-to-end performance will be the minimum of the performance of this link and of that link, and this is on a wired network, might give you good performance. So that's another motivation here. So such a gateway is called a web proxy here. You might remember from the first course when we discussed the TCP-IP architecture, I sketched that before TCP and IP were created, before packet switching was invented, computer networks and the first version of the internet, that was called the NCP protocol, was a store and forward system. We send a message to a computer that analyzes it and decides where to send it. So this is, in some sense, what is happening here. And this is against the principle, the design principles of the internet. Let me skip this. The illustration I've shown of an application layer gateway, it's against the principle, but as we will see, it's still usable, like many things that are against principle. The thing I've shown was ignoring security. So it's the very first form of a web proxy that simply repeats the GET message. But in practice, any access to the internet today is by first using TLS. So if we combine TLS into the web proxy, we obtain what is called an HTTP tunnel. So an HTTP tunnel, the story starts in the same way. When I connect to the internet, in fact, I connect to the HTTP proxy, and my web browser is configured to know that there's an HTTP proxy. So whenever I send something, for example, I want to go to a given server here, my system will first connect to the HTTP proxy. That's opening a TCP connection. When the TCP connection works, I will send a special HTTP message, which is connect to this address here, that will cause the proxy to open a TCP connection to the final server. So it's similar to what we had seen before. But only then, when this connect is okay, now my host knows that the end-to-end connection works, and then I will use end-to-end the SSH, the TLS connection. Because of course, we don't want the web proxy to know all of our secrets here. So the web proxy here is not having any of the key cryptographic information. So when I open those two connections here, the data is piped from one connection to the other, in particular, the data that is encrypted here, which means that the encryption is truly end-to-end here. So this is how HTTP web proxies are used today. I mentioned that application layer gateway are against the principles. Well, this has received a name in the internet folklore. It's called the end-to-end principle. So the end-to-end principle says that if you're designing something in the internet, you should try to do it end-to-end, which means in particular, you should not have intermediate systems of layer other than MAC and network layer. So you should not have transport layer gateways or application layer gateways like we're showing here. This is really fundamental to the design of the internet, which means if you would use this principle for mail here, in fact, we don't use the end-to-end principle. If I send a mail to you from my smartphone to your smartphone, I am not opening a TLS connection between my smartphone and your smartphone to send the message here, right? In fact, we send it to the mail server. So that's one of the examples where what would a strict application of the end-to-end principle mean? Well, it would mean, just like as I was saying, it would mean that we send directly here a TCP connection from host to host, but there's even the reasons for this not to be a good idea, primarily because the end host is not expected to be on and working at the time. So my smartphone is probably sleeping now. So if you try to open a TCP connection to it, you will not be able to do it. Plus, you would need to know, you need to have a server here in this system, which needs, and this is probably behind a NAT. So having a server behind a NAT, as we know, is not something very comfortable. Plus, there is security. If you open a server on the internet, you will be bombarded by malware instantly. So that's all of those reasons make it undesirable. This is why we have web servers, but we have mail servers. But the end-to-end principle essentially is saying that between mail servers, you should go directly. So you establish TLS or quick connections between mail servers to transfer the mails, but you don't go multi-hops here. Except if you do it for filtering mails and etc. We know that EPFL, when a mail comes to the Outlook server of EPFL, before getting into that, it goes to a mail cleaner or some other type of server that will analyze all the emails, kill all the spam, and only do it. So security is one of the major reasons for departing from this principle. Voila, we do a break and resume at 1:15. We will see several uses of application layer gateway, but here is one which is very frequently used. It's the equivalent to the web proxy or HTTP tunnel that I mentioned before, but on the server side. Assume you're running a data center, so you have interface to the outside. People can connect to your data center. For example, your Google. You send a query to Google. Now, what does Google do when you send a query? Well, it puts the query into a huge farm of computers that contain all the information, all the indexing information of Google. That's shown here. And the result of this query will be returned to you. Your query does not natively go directly to the server farm of Google. It goes by an intermediate layer, which tries to balance the loads. So it's called a load balancer, in order to control the amount of work that those things do. So such a data center requires a load balancer to avoid, to have good performance. Otherwise, you will have a few servers that will be congested and a number of them that will be underused here. A load balancer, here I'm showing two, gets a query or a message and decides to which computer it is sent here. How could we split the traffic between the two? So here I'm showing two of them for reliability, because I don't want my load balancer to be a single point of failure. How could I obtain that data coming from Lisa or Bart goes to load balancer 1 versus load balancer 2? So how can we balance the load balancers themselves here? We could use the DNS. That's one of the possibilities that is used, but most systems use something else that we've seen with OSPF called equal cost multipath routing. So typically what will be done, instead of using DNS, because it's more lightweight, is to give the same IP address to all load balancers, inject into, here there's the internet, but just before the internet, there is the infrastructure of routers of this data center. So there is a little OSPF here if you want. So the local OSPF here will have the same IP address that is attached to multiple points in the network here, which we have seen is something that can exist in OSPF. For example, when we use multiple areas, that's exactly what happens here. But it can happen with physical machines that have the same IP address. Of course, those machines have multiple IP addresses. With IPv4, it's not so common, but with IPv6, it is the rule. So they have a usual IP address, which is used if you talk to the machine, if you ping the machine, if you set up some software into the machine, you will use the IP address, that's the normal one of the machine. Plus, it has another IP address, which is, for example, www.google.com. Or the name, the IP address that corresponds to this here. And then inside the OSPF, we've seen that we can do load balancing at the network layer using equal cost multipath routing. So that's a typical combination of DNS and equal cost multipath routing that is used here. Another application is, for example, separating a network between different zones. For example, EPFL is separated between a number of zones. Here is a simplification of what happens. We can have an intranet zone and an untrusted zone. The untrusted zone is the part of the network where you have the servers that are exposed to the outside. And the EPFL zone is the zone that contains the servers that you don't want to expose to the outside. For example, the servers that do the accounting, the SAP servers for transferring funds between accounts and so on. You can access them only if you are inside EPFL or if you access EPFL via the VPN. But of course, the web server, if somebody publishes something on the internet, you want this to be accessible to everyone, not just those who are on the VPN. So this is typically done by having filtering routers that separate by putting filtering rules in routers to create zones. For example, here, the filtering router in R1 will allow only traffic to go into EPFL that has a source IP address that is inside EPFL. If we come from the outside, you will not be able to go here. You will need to go to be inside, which can happen via the VPN, but cannot happen natively here. But the filtering rule of R2, for example, will allow all traffic that is going to one of the servers that is exposed in the untrust zone, and only this. It will not allow, for example, someone to send a packet to another address that would be here and have this packet enter this domain here. So the combination of filtering rules and application layer gateways or servers that are in given zones are what is called today a firewall. And firewall in your and my computer is simply some software in the computer. At the stage of at the scale of a company, a firewall is something like this, for example. What is the implication in terms of protocols? For example, if we go via a load balancer here using equal cost multipath from host, from client, final client to load balancer to server, assume the load balancer, in this case here, is an application layer gateway. Right? So it gets the HTTPS query, it terminates it, and dispatches the job to something here and get the reply and sends it back here. Assume we lose a packet here on the path here. Which system will retransmit it? I close the poll in a few seconds. And the correct answer is A, the load balancer one. So even though the traffic might be going apparently from the system that provided the answer, it's relayed here at the application level. And since it's relayed at the application level, there are two TCP connections or two quick connections. It doesn't change anything here. So the retransmission will be done by this. So now it's time to start discussing one of the underground things that were visible in Lab 3. In Lab 3, we had already servers that were running IPv4 or IPv6. And that's one of the things that will accompany the evolution of the internet for the next decade, probably, or even more, because we see that the deployment of IPv6 is very, very slow. Even places like EPFL that are supposed to be high-tech did not want to deploy IPv6 on Wi-Fi, so they didn't do it until I insisted many years after years. It's only a change of vice president that made it possible. So you see that many companies will not do it simply because they don't understand what's the benefit. And it's true, there is no selfish benefit into moving to IPv6 if you have something that works perfectly well with IPv4. So IPv4 will continue to work for a long period of time. We see also that with NATs, we can reuse the IPv4 addresses as many times as we want, so it will continue for some time. But we will have a world where some part of the world runs only IPv6 only. And then the question is, how can we have a machine that goes to servers that run on IPv4 only, servers that go on IPv6 only, and servers like the ones of EPFL that run both IPv4 or IPv6. So in a case like this, if Lisa has both IPv4 and IPv6, if the EPFL has both, and if the network between the two has both, probably it will prefer IPv6 because that's the most modern thing. So that is an easy part here. But how does Lisa know whether she should be using a socket IPv4, IPv6, or how does the software in Lisa's system know whether she's going to a server that is running IPv6 or IPv4? In the lab, you had exactly this problem. So if we scale this to the real world now, not to lab 3, how can we know? Let me close the poll in a few seconds. Closing. And the majority says B. And this is probably a bias that you have because you did lab 3. So in the lab 3, we had a server that is, we don't know exactly what it's doing, so you try. But in the real world, we won't do this. You do this if you're in an experimental world or if you have a good purpose, good reason for doing that. You don't want to do this in the real world. I mean, you're going to something called newstuff.epfl.cn. That's a new branch of EPFL in China. And you don't want to try first with IPv4, then with IPv6. Perhaps both will work, so you will overload the world by trying lots of things. That's not very efficient. So we probably don't want to do this. We could try to do this, but ping does not always work, so it's not a reliable method either, because many ping messages are discarded for security reasons. The correct answer is the DNS. It is the DNS here that will help us know whether the service we have is available on IPv4 and IPv6. Remember, we saw that in the socket programming examples. You can do a get host by name, and you will know whether the host has IPv4 or IPv6 or both. So this is exactly what Lisa's machine will do. In this case, it will return only a quadruple A record, which means the only address I have is an IPv6, and the software now knows, and it will either use a dual stack socket or a native IPv6 only socket to reach this one here. As you know, probably DNS can be accessed via IPv4 or IPv6, so DNS in itself is independent, as an application layer, is independent of the networking layer on which it resides. So even if your DNS server is v4 only, it's quite possible to obtain all answers for IPv6 addresses. So there is not an IPv6 DNS and an IPv4 DNS. The DNS contains all IP addresses in one big file here. Now, this can be used to solve problems which are less nice than what I showed before, where we don't have end-to-end connectivity. So this can be used to solve what is called the interworking problem. The interworking, so there are two types of problems in the transition to the interconnection of IPv4 and IPv6, which I call interworking and like-to-like. Interworking means I have a host that runs only IPv6, perhaps because I'm running on a cellular network that delivers only IPv6 addresses. And somewhere in the world, perhaps EPFL a few years ago, has only IPv4 service here. Or you speak over IP telephony to a device that supports only IPv4. Or vice versa. You have an old host, an old machine that works only IPv4. For example, some telephone that's sitting in an elevator, it has only IPv4. It was put there a few years ago. Nobody cares about changing it. So that's the interworking. We want a host of one type to talk with a host of another type. As we know, IPv6 and IPv4 are not interoperable. If you send an IPv4 packet to a machine that speaks only IPv6, the packet will be ignored. It will not be parsed correctly. That's different from what I call like-to-like access, which is an easier but equally important problem, which consists in having an IPv6 machine, for example, speak to an IPv6 machine when there is not an end-to-end IPv6 connectivity. That's a problem that exists less and less because most providers provide both IPv4 and IPv6, but it continues to exist in corners. For example, in the smart grid project, I was unable to convince the rest of the project to do everything IPv6 compatible. So it works only with IPv4. So when a PMU, phasor measurement unit, the VPFL sends data to one of the servers that collects them, they speak only IPv4. So if you want to connect to the PMU and your host is on IPv6, so they speak only IPv4. Now, if at some point in time the rest of VPFL has only IPv6, then you have a problem. So like to like versus interworking, there are different things. This is a networking problem. How do I carry IPv4 packets over something that is not end-to-end IPv4? That's a relatively easy problem. This interworking is how do I translate an IPv4 stream of packets into IPv6? Yeah. Now, translation, interworking, there is a stupid but very simple and efficient way, not so efficient, but simple in the sense of deployment way of achieving this, which is to use application layer gateway. After all, if I have a web proxy that works both on IPv4 and IPv6, then I can show an IPv6 face to IPv6 customers and an IPv4 face to an IPv4 server, for example. So that solves exactly the problem. The logic, of course, I need to put something dual stack here, but that is a problem that's much easier than changing all the network or all the hosts here. So for example, if Homer is sitting on an IPv4 only device and it uses an enterprise that uses a web proxy to force people to go through the web proxy before surfing the web, then it will work perfectly if the device is IPv4 only. Because when we go at the layer of TCP, whatever layer was below is completely hidden. So the application will be able to handle both. So that is one way. It's called an application layer gateway 4.6, in the sense that's one that has both IPv4 and IPv6. So this application layer gateway needs to be dual stack. It's a host that has both IPv4 and IPv6, and it must be connected to an IPv4 network on one side and an IPv6 network on the other side. Yeah. For example, for many years, EPFL was running, before it moved all its services to Cloudflare, it was running it on its own servers, and the servers were, of course, IPv4 only, because who would move everything to IPv6? So it was running on IPv4 only, but it was reachable over IPv6 by using an application layer gateway. So if you had IPv6 only, you could still go to www.epfl.ch, but in fact, you were going to another machine called www.6.epfl.ch that was running, working as an application layer gateway. So you were opening your TLS connection that was tunneled here to this other thing by going through this intermediary point here. How does this machine know that it has to go here rather than there, right? Well, again, the answer is with DNS. If you do such a trick here, you have to put in the DNS records for the IPv4 address of your service and the IPv6. Then it's very simple. You put, for the IPv4 address, you put this one, and for the IPv6, you put that one. So whoever connects to this service and has only IPv6 will get this address and will go to this application layer gateway. Whoever has IPv4 only will get directly the IPv4 address and will go directly to this machine without using the gateway. Now, what happens if you're dual stack? So you have both IPv4 and IPv6. This service exists natively and on the gateway. What will happen to you? close the poll in a few seconds. And the majority says it depends, which is a very safe answer. Many systems will prefer IPv6. I mean, if you put yourself in the shoes of the designers of the operating system, so you work at Apple or Microsoft, and you see, I have a service here. I go to DNS, I find an IPv4 and an IPv6 address. Then many systems would tend to prefer IPv6 because it's more modern. The most recent thing is so that is what is done or was done for many years by many systems, which means if that is what happens, I mean, Lisas will go via the gateway, which probably slows down the performance. The gateway has probably been designed as a hack to get rid of Professor Le Boudec, who always complains about not being reachable on IPv6. So most traffic is expected to go to IPv4 here. So we have the paradox here that if you use natively IPv6, I did this experience a few years ago at IPv6 on my desktop, and the performance was very bad, in fact, because my Windows machine was natively using IPv6, was preferring IPv6 statically over IPv4 when both were available. So more modern machines, I don't know about Windows, but I know that macOS does it, tries to keep a record of the performance. Not clear to me how they do it. So they have some kind of heuristics to decide whether they will use IPv6 or IPv4 for that. But that's a problem that you cannot solve optimally with certainty anyhow. Most of the time it is true it will be better to use IPv6, but not always, and it's not easy to decide. Voila, that's the end of this module on the application layer. In fact, we have not spoken very much about applications, but all things that go around that. Other questions? Now we move on to all the ugly things that is better not to teach from the beginning, because otherwise you don't understand. So that's what I call deviations. So a very complex system made by humans is always based on principles. That's the only way we're able to do very, very complicated things. We need principles. It's the only way you can move people. You need religions or dogma or ideology to move people together. So same thing to run, to make all these hugely complex software systems, we need principles, and we have seen a number of them. But then when you do the principles, there's the reality that forces you sometimes to deviate from them. And as I explained already at the beginning of this course, I organized this course to first teach the principles, and as we need to explain the deviations, we explain them as deviations. The big deviations, for example, is the NAT. The NAT is something that is completely orthogonal to the idea of the architecture, should not exist, but it still exists today and is very familiar. And if you explain how a router works by assuming a router is a NAT, then things are very complicated. So we will see here a number of deviations of the architecture. In fact, all those ones, we start with proxy ARP, we'll finish with MPLS. So let me start with proxy ARP. So the principle that it violates is one subnet is one LAN. Means one subnet, what IP software views as a subnet, should be something that the communication layer of the MAC layer truly makes as a subnet, which means all the packets should be able to travel from one host to another in this local area network via bridges or Wi-Fi base stations. Assume you violate this principle, and you do, for example, the configuration as shown here. I have the subnet 12.12.12 here that is attached on this, is here between R1 and R2. And I create another machine that has this address here, but it's not at all at the right place here. So I have a subnet here, which is a LAN. There is a switch, Ethernet switches between R1 and R2. There's a number of servers or machines that are connected. They're in the right place. And we see correctly that the router R1 has a routing table that says in order to go to this prefix here, it's on link here. But there is this problem, there is this thing that is outside here. So the first thing that will not work is that if I send a packet, for example, that reaches R1 to this destination, I should not conclude that it is on link, which is the correct thing that would happen otherwise. So one way to fix it, or one element of the fix, is to add more specific routes by treating this as a subnet of this one. If in the extreme case, I call this a host route, I can put an entry /32 with IPv4. It means it's all the bits of this address. And I say it is not on link, but it needs to go to R2. So I can do this here. And then it will have the effect that the packet sent by R1 to this address will not be treated as if it would be local, which means I would do ARP, find the MAC address, put the corresponding MAC address. Instead, it would be sent to R2 here. So that's one way to solve the problem. However, it will not work if there is a host A that's in between R1 and R2. There is an Ethernet network with one or several switches here. So presumably there are other machines that are running here. Now, what will happen at A? Well, we solve the problem by changing the routing tables in all routers. So if we want to do the same thing, we would need to change the routing table at A. But typically, we don't do this because the hosts don't participate in OSPF. You don't want the host to run OSPF, which is a solution. Sometimes it is done not with OSPF, but with RIP, which is very simple. Sometimes you run RIP in the hosts to configure the routing tables when you have such weird things here. But typically, this will not be done. And if this is not done, what will happen? There will be a problem at A. Because if A has a packet to send to this machine here, A will analyze its subnet prefix, decide it is local, will send an ARP request to this address. And of course, it will not get there because ARP requests are never forwarded via routers here. They're always contained in the local area network here. So the ARP request will die, no reply will come, and the red machine here will be unreachable. Except if we add another fix, which is called proxy ARP. Proxy ARP, or proxy NDP for IPv6, consists in saying that it is the router that will answer the ARP reply here. So when A sends the ARP request here, then R2 is configured to do proxy ARP for A here. Now, is it simpler than to fix the problem? Probably not, but it is doable because routers are under the control of the network administration. So if we violate things in a way, we can set up routers to do this. So this is what router R2 is programmed to do. So when A will send an ARP packet saying, what's the MAC address of this? R2 will reply, and R2 will reply by giving its own MAC address. Because R2 knows in order to reach this thing here, it has to go via me, or at least that's a possible way to go via me. If R1 would do it, the packet will go to R1, but R1 knows how to send it further through its routing table. So the problem would be solved also, not efficiently, but would be solved here. So this function is called proxy. R2 is doing proxy ARP for this machine. Proxy, as we saw the web proxy. So the concept of proxy is a machine that impersonates another machine. So here, R2 pretends to be this machine. That's the concept of proxy from the ARP viewpoint here. So here's another usage that is done at EPFL when you reach EPFL over a VPN, at least with the previous configuration that we have. So here I have a machine at home that accesses EPFL via VPN. So my machine and the VPN server of EPFL establish what is called the VPL tunnel. We'll discuss that next week. And allocates to me an IP address, which is an IP address of EPFL. So this is how the VPN lets you operate as if you would be inside EPFL. So I have an IP address of it, but of course, in reality, I'm sitting at home on my Swisscom network. Right? But through the tunnel, I have another virtual interface with this interface with this address. And if you look at the prefix here, you see that this address is in fact as if it would be on this subnet here, which is a subnet on which the VPN server of EPFL is sitting. So we have exactly the same problem we have here, and this VPN server is in fact acting as a router. So we have a subnet here and an address that is not belonging to, that is allocated to a machine that is not at the place where it should be here. So what happens when there is a packet that has to go from this machine to me at home here? So this router, if it sees this address for the first time, will send an ARP request, and the ARP request is asking who has the MAC address corresponding to this here. What is a plausible answer of what will happen? I close the poll in a second. Closing. And the majority says A, which is the correct answer. So B would mean that it does proxy ARP, but it gives the MAC address of GreenMAC. Now, the MAC address of GreenMAC is not useful. I mean, GreenMAC has an Ethernet address locally. Now it's accessing the tunnel doesn't have a MAC address. So this MAC address is completely of no use to anyone who is not on my local area network at home. So it's not useful. GreenMAC replies with its MAC address. It will not be useful. Plus, it's probably not doable. We don't want to send ARP queries all the way through the VPN tunnel to me. So the only meaningful thing is this one. And this means that this VPN server, when it allocates an IP address of EPFL through the tunnel, it has at the same time to do proxy ARP. So that's a very common use of proxy ARP here. Voilà, that was our first violation. Now, another thing which is not truly a violation, but is a weird and ugly thing, fragmentation. We've mentioned this fact already. Now, let's look at it in more details. The problem is that not all packets have the same size. Historically, there were good reasons for that. There were very different technologies. Like, for example, there are local area network technologies that have very, very large packet sizes, but that tends to be exotic today. CERN has things like this when they do high energy physics experiments. They have huge amounts of data to transfer, and they make bigger packets because the processing power required by routers is less if the packets are bigger. When you transfer monstrous data, it's the larger the packet, the less the CPU of the routers and other machines is loaded. But that tends to be exotic. On the other end, there are, if you use ZigBee or other Internet of Things protocols to communicate between thermostats and a server that controls the temperature of a thermostat at home, probably it uses very, very short packet sizes because the link speed is kilobits per second, not megabits per second. So at kilobits per second, even a big packet is large already. So you want the packets to be small. And that if you do IP over ZigBee, then you have a small packet size here. And we've seen that if you do a TCP connection, you want to negotiate what is the packet size so that you have a packet size that fits all the way. Now, this tends to disappear. If we do ZigBee, we will tend to do special things. We will do the ZigBee gateway that will not do an end-to-end TCP connection between my radiator thermostat and my application that's controlling it here. So most packet sizes today are around the 500 byte, 1500 bytes. However, it is not possible to fix a packet size that's unique, a maximum packet size that's guaranteed to be valid for all systems, because of one good reason that we've just discussed when we discussed the VPN tunnels, encapsulations and tunnels. If I send a packet, we will discuss tunnels in detail next week, but a tunnel means that I send an IP packet inside a TLS connection For example, that is connected between my VPN client and the VPN server. So if I do Wireshark at all levels, I will see my end-to-end IP packet that is inside a TLS connection and is treated as data. This TLS connection itself is over TCP, which is inside IP packet. Every layer costs an overhead that reduces the packet size. So over a VPN tunnel, the end-to-end packet size is much less than the 1500 bytes here. So first thing is that an interface here must have a packet size which is not always the same. Here I'm showing on my machine at some point when that was a Windows machine. Here I'm showing three interfaces that have different packet size. That's the standard Ethernet or Wi-Fi interfaces. Here there's another interface that has a smaller packet size, essentially because it uses IPv6 in a tunnel that we will discuss next week. And here's another one that has a huge packet size, well, because it's the loopback interface. The loopback is the interface that we use for testing servers, for example, that we've used extensively in the lab. This one, there's no reason to limit the packet size because there's no packet. The data goes from the operating system to the operating system directly. So it has typically a huge maximum packet size. Now, why do we discuss this? What is the problem? Well, here's an example where there is a problem due to different packet sizes. Well, typically, it's easy to understand. What happens if I send a packet that is too big for some part of the network here? Right. If I'm sending a packet from A to B, and in between, there is a packet size that is less than the maximum. Now, to be optimal, I will have a tendency to send packets that are as large as possible. That's what we do with TCP negotiation of the maximum segment size. We open the TCP connection. We agree on the packet size to transmit. Now, if TCP has a big bulk of data that needs several packets, it will create packets that are as big as possible. So it will create maximum size packets. And what will happen here when those packets hit this network that is not able to carry them? Well, we will have what is called fragmentation if that happens. With TCP, we should try to avoid it. But if that must happen, we will fragment. So how does fragmentation work? Fragmentation could have been done at an intermediate layer, but is not. It's done at the IP layer. That's an old decision of the IP architecture, which means that if I have an IP packet that is too big here I'm taking round numbers that are easy to analyze. Assume I have 1400 bytes of data and 20 bytes of IP header. When this packet reaches this router here, this router will say, I need to forward it to R2, but it is not possible, so I will break it into packets that are able to fit on this. MTU 620, that means the packet can have at most 600 bytes of data if there is no option in the IP header. So I will break this packet into three that are as big as possible, and the last one is smaller because it's not a round number. I will create three packets. Now, those three packets are three independent IP packets, and the information is kept in the IP header that there was a fragmentation. This is why we have in the IP header fields that are called length, identification, and some offset and a flag. The length is the length of the packet here. So at point 1, the length is 1420. At this point, the lengths are 620 or 220 for the last packet. And then there is a field called identification. Whenever a source creates an IP packet, it puts a number into the IP packet. So the main use of this number is for this purpose. So when this packet was created, it had this number. So this number means nothing other than all the different packets that have the same number are fragments from the same original packet. So when this packet is broken into fragments, the fragments inherit this identification number. Why is that used? Well, because those packets are independent packets. They will be carried by this network, which may have multiple hops. Then each of those packets travel this. Hopefully, there is per-flow routing that makes sure that they all go through the same route, so they will arrive in sequence. But this is not guaranteed. So they will arrive at R2 that will send them to the destination. R2 will not reassemble. Routers never reassemble packets. It's not their job. Why? or because it's a major pain to reassemble packets. It's a major pain. The packets have been broken into three. When you reassemble, you have to handle a case of what happens if the second fragment is lost, for example. If the second fragment is lost, then the whole thing is lost. But how do you know if the second fragment is lost? Well, it's the same problem we have with TCP, right? Knowing that detecting a loss, you need to detect the loss. The fact that fragment 3 arrives before fragment 2 does not necessarily mean that fragment 2 is lost. So you need to keep it into memory. You need to start a timer. This is very complicated. It's host operation. It's not router operation. So you don't want to put that burden on routers. So you don't. So the 3 fragments will reach the destination, and then it's the host operating system of the destination that will receive these 3 packets and will reassemble them. In order to reassemble them, it will glue them by the identification. And in order to know, for example, that 3B is the second packet, there is an offset in packet 3B that says the offset is at byte 600, and in packet 3C, it is at byte 1200. So we know that this data here should not be reconstructed at the beginning of the packet, but at an offset of 600, which is corresponding to the number of bytes that were before. So there's an offset 0 for here, 600 here, and 1200 for that. Now, if you do a Wireshark of the packet, you will not see 600 or 1200, but this divided by 8. Why divided by 8? Well, this gains 3 bits when you encode this in binary. So it's just to simplify to gain 3 bits, because this is an IP header. An IP header is an area where bits are expensive. And then the offset is not sufficient, because if I receive those 3 ones, I still need to be able to know that it's complete here. Perhaps there was a 4th fragment that is lost. How do I know this? Well, I will know it only if I receive it, or if I know here by putting a flag in the last fragment saying it's the last one, which is the more bit here. More bit equals 0 means there is not more to come. So it's equivalent to saying I am the last one. So the offset plus the indication of the last allows the destination to reassemble. But of course, with all the complication that I said before, it needs to wait until everything is received, and there might be performance problems associated with that. A question related to TCP now. What happens if a fragment is lost? I close the poll in a few seconds. And the majority says B, which is the correct answer. Because fragmentation is done at the IP layer, if one fragment is lost, then the IP layer will not be able to reassemble, will try, will time out, and then will discard the packet and saying this is lost, which means that TCP will need to retransmit the three fragments. Yeah, that's the inefficiency. TCP plus fragmentation, they don't work well together. And this was, in fact, you remember in the mid-80s, there was a collapse of the internet due to the absence of congestion control. This was amplified by exactly this. There was a lot of fragmentation that was happening. And whenever a packet is lost due to congestion, for example, or if one of the fragments was lost due to congestion, then the source would retransmit the 3. So when the network is congested and does not have enough capacity to transmit the 3 fragments, we retransmit the 3, which makes congestion even worse. So of course, we want to avoid this. So fragmentation should be avoided in the internet. So the first thing is that all applications should try to avoid fragmentation by estimating the path MTU. So how can this be done? The path MTU is typically done with these 7-letter acronyms that most modern operating systems should implement. you observe the largest possible path MTU that works between flows that you have observed. So typically for TCP connections or for long-lived UDP interactions, you start with a possible path MTU that you think works, and then you try to increase it. For IPv6 mandates that all IPv6 implementation must have an MTU as large as this here. For IPv4, this is not mandatory, but in practice, we start with this value here. So when we do path MTU, we start with this, at least for most systems. Perhaps your radiator thermostat will start with 68, but other software will start with this value here. And TCP connections should, of course, always refuse to have MSSs that are larger than what has been estimated by the TCP. I forgot to mention that the fragmentation that we have seen here works only for IPv4 routers. So IPv6 routers, when IPv6 is redesigned, people say fragmentation is really a bad idea, so it's forbidden for IPv6 routers. Not necessarily at the source, but IPv6 routers will always, will never fragment the packets. It's only IPv4 that will do it. But with IPv6, we could have fragmentation at the source if, for example, you use a UDP application that creates a packet that is not following this, then fragmentation will occur. Voila, that's all for today. 1 minute delay. I didn't hear the ring. Was there one? Yes. Okay.